degrees from the University of Galati and from Ovidius University in Romania. His currently active research topics are exergy analysis of complex systems, the CFD-aided optimization of energy conversion components, the design and prototyping of ultra-micro gas turbines for hybrid vehicles and portable power generators, and the application of AI techniques to turbomachinery design. He has authored or co-authored 4 books, 2 in English, and over 200 scientific papers. So please welcome Professor Sciubba. And,
then I can change it myself.
Probando, probando, probando.
Good afternoon. Do you hear me? This thing working? What about Irapuato? Do they get the signal? Low. I can go ahead? Okay. So, good afternoon. This workshop is meant as a series of relatively unrelated topics that all are introductory topics to what I'm going to discuss tomorrow in my lecture. So what you might find is that, can you turn off the lights please, otherwise, dim the lights. If you look at the topics here, laminar and turbulent flow, viscous drag, entropy generation rate in a flow, pipes with permeable walls, circulatory systems, branchless supply, all of this might seem like haphazardous to you, but really leads to the topic of my talk tomorrow, which is a discussion of a general law which rules the branching of capillaries in human structures, plants. Okay? So you have to bear with me that these topics are introductory to that, though they may seem separate from each other. I have one request of you. If you don't understand something, raise your hand and ask. Okay? It's better you ask instead if you stay with a doubt and nobody asks a question and then some topic remains completely unclear. Okay? So please ask. If you don't feel confident with your English, you can ask in Italian, in German, or in Spanish. Okay? So you are free. Now, laminar against turbulent flow. You had fluid dynamics. Laminar flow, everybody knows what laminar flow is. Laminar flow is a flow where you have streamlines. It's so nice. Streamlines flow always in one direction. They curve all together. They don't cross each other. And they behave like really nice citizens. Turbulent flow is some more chaotic. There is no streamline. The fluid behaves randomly. There is no nice velocity profile. And there are different properties of this flow. Of course, why am I introducing this topic? Because I'm interested in blood flow. Blood flow is laminar in smaller capillaries, is turbulent in the aorta and in the major veins. And you know that it's turbulent because when you feel your pulse, you are making the fluid turbulent by obstructing it. Okay? also when you do like this, okay? You can do it also under your armpits or everywhere you want. However, the idea is that you are obstructing the flow, and behind the obstruction, you get a turbulent flow. So, turbulent flow is important because if we want to discuss the flow in natural systems, we have first to understand whether it's laminar or turbulent, and then to discuss its typical characteristics. Now, what is the typical feature of turbulent flow? Well, this is laminar flow here, and you put a drop of red ink, and you will see that this red ink becomes transported nicely along a streamline. This laminar flow. After a while, something happens, and you get a red spot, which is becoming more and more diffuse until you lose the red, because it's been completely dispersed into the flow. Who did the dispersion? The velocity. Because the velocity is no longer in this direction and uniform, but it has what are called the fluctuations, velocity fluctuations. They appear in turbulent flow. So the velocity in this direction may have an extra velocity here and a minus velocity here. Or the vertical velocity may have a lower velocity here and a higher velocity here. These V prime, U prime are called velocity fluctuations, and they are typical of turbulent flow. They are absent in laminar flow. What identifies the laminar flow, the laminar and turbulent flow? We used to say Reynolds number. What is the Reynolds number? Reynolds number is a number that expresses a similarity. It's a ratio between two physical forces. On the numerator, you have a quantity which is proportional to the inertia force. On the denominator, you have a quantity which is proportional to the viscous force. Okay? So, if the Reynolds number is very low, it means that you have a very high denominator, very high friction force. Okay? And the flow is usually laminar. Why? Because friction is screwing up every will of the molecules of the fluid to go somewhere else. Okay? On the other hand, if you have supersonic flows or very high speed flows, then the viscous portion is many, many times, orders of magnitude smaller than the kinetic energy and the acceleration of the inertia force of the fluid. Okay? So high Reynolds number, low Reynolds number. We say high Reynolds number is turbulent, low Reynolds number is laminar. There is a frontier. Fluid dynamics book always say 2000 is the number, magic number. You have a laminar flow, Reynolds 2000, turbulent. That's not true. Nature doesn't work like this. Nature works never by steps. There is no heavy-side function in nature. There are only nice S-shaped transitions, okay? Even in explosions. Now, what happens is the Reynolds number up to, let's say, 1000 remains laminar if you don't disturb it too heavily. Above 2000, it's almost surely turbulent unless you take special care of avoiding disturbances. Between 1000 and 2000, whether it becomes turbulent or not, the flow depends on the boundary conditions. So this is a more clear region explanation of the laminar to turbulent transition. We will see later some slides which illustrate. What are Reynolds number in nature? A baseball thrown by a professional, so fast, a fastball. Reynolds 200,000. A small pipe, like 1 centimeter diameter, from 500 to 2000. So it can be laminar and can become turbulent. A river, 50 million, very high. A car traveling at 130 kilometers per hour on a highway, 10 million. Ocean currents, 50 billion. Wind turbines, 100 million. it's clear that all of these three flows, also the river, will be turbulent for sure. There is no way you can make them to be laminar. They will be turbulent. Pipe can be laminar, can be turbulent. Now, what are the flows in natural, like in the blood? Aorta, 3000. It's turbulent, as a matter of fact, because it's close to the heart, and the heart is pumping. So the blood is undergoing a unsteady motion. So it's very easily made turbulent. And in fact, in the aorta, you have turbulent flow. In the capillaries, 1/100th, the flow is definitely laminar. In the sap of the plants is carried from the roots to the leaves at very slow velocity by capillary action and ionic action. So it's Reynolds number very low, laminar flow. Micro heat exchangers. You know, the chips, electronic chips are now cooled, or actually we are trying to design heat exchangers that may cool electronic chips in supercomputers. And the heat exchangers are this side, the side of a chip. Okay? They are stuck underneath of the chip and have to take away to absorb the heat that the chip generates. Now, the heat exchangers have microchannels, and the Reynolds number in microchannels is about 500, less than 500. The flow is laminar, and that poses problems because laminar flows have lower heat exchange coefficients. So this is the idea of laminar to turbulent difference. But let's see what the characteristics of the fluids are, of the flows are. The turbulent flows are random. We'll see in what sense. They are 3D. So when those of you who deal with numerical simulations of turbulent flows and do these nice simulations with fluent ANSYS or CFX of a two-dimensional flow over a wing, you are doing bullshit, because there is no turbulent flow in 2 dimensions. It doesn't exist. Turbulence is 3-dimensional. So when you do this, when you go, we use Fluent in my group. In the manual, the tutorial manual of Fluent, there is a nice example of a wing in 2 dimensions. And then they use a K epsilon. And this is a distortion of the reality, because there is no 2-dimensional turbulence. Turbulence is by nature 3-dimensional. There is only one flow, which is 2-dimensional in turbulence. Anybody knows what flow I'm talking about? Guess. No. You thought you knew. In the atmosphere, there is a level at about 10,000 meters where you are far away from the mountains and where the flow is very fast, and it's 2-dimensional on a spherical surface, of course. Okay? So it's not a flat plane. It's a spherical surface. And these are the high stratospheric winds, which can take up to 200, 300 kilometers per hour. And the turbulence there is 2-dimensional because there is no disturbance from below. Okay? But there are otherwise no 2D turbulence. The turbulence, another quality of turbulence, turbulent flows have vorticity. So either they produce or destroy, or at the same time produce and destroy vorticity. What is vorticity? Vorticity is the difference, you have had that in fluids 1, the difference between the derivatives with respect to x and y, respectively, of the velocities u and v, du over dx minus dv over dy, which means that the differential of velocity in this direction is compensated by a negative differential in this direction, which means obviously that the flow is going like this and like this. So it's what we call a vortex. Okay? But don't expect to see vortices like this in a turbulent flow. This is an idealization that we have in textbooks or in figures or in calculations. The turbulent flow is basically a random flow. So what you see are structures that may seem roundish, but they are not, maybe elongated, but they do not look like this exactly, except at very large scales. Okay? Now, large Reynolds we have talked about. Now, how do we represent a turbulent flow? We represent it by dividing the velocity which we measure at an instantaneous moment into two components: a steady state or average velocity and a fluctuation. So the actual velocity at each instant of time is made up of a component which is an average, suppose stays steady, but it can also move, it can also change in value, though not randomly. It's a smooth function, and by some randomly looking oscillation, u prime. And the fact is, if you take the averages of these fluctuations, the average is zero. And I will show you in a slide later why it is so. The averages of the turbulent velocity fluctuation, pressure fluctuation, temperature fluctuation are all zero. But their squares are not zero. And the reason is physical. It can also be shown by mathematics, but the reason is physical. What is u prime u prime? It's u prime squared. It's twice the kinetic energy of the turbulent scale. So why should it be zero? If that is zero, then you have no turbulence fluctuations. Okay? Because the square must always be positive. So if that is zero, it means that u prime is always zero. But if u prime is always zero, then the flow is laminar and not turbulent. So the u prime, that number there, is always different from zero. Not everywhere, but in the field is different from zero. Okay, I have some examples. This is, you remember the Exxon Valdez accident? The tank ran on shore in Canada, I think, and it spilled tons and tons of oil. Now, we are not discussing the spillage, we are discussing this picture. This is the tank, and the current in that time was obviously coming in this direction. This is the spilled oil. And this is what we call a turbulent wake. What happens is the oil is spilled from the boat, and the ocean carries in this direction. But the oil, which stays on the surface, so yes, in a sense, this is two-dimensional turbulence, gets some energy from the ocean and starts dissipating its velocity with this turbulent wake. This is a typical shape of a turbulent wake, and actually it has many characters which are common to other wakes. It enlarges very much, so the diffusion in the direction perpendicular to the mean motion is very high, and it has fluctuating diameters. So see, this region is laminar, this region is laminar, this region is laminar, this region is laminar, but on the average, the whole thing is growing up. Okay? So this is a typical case of high Reynolds number wake. This is cigarette smoke. You smoke? Yes, you do. I smoke. I don't smoke cigarettes. I smoke cigars. Okay? But this but the smoke is always, I mean, the behavior is always the same. What happens here? The smoke raises because of buoyancy. The smoke is hotter than the air, so it rises up slowly. But in doing this, it cools down. And at a certain point, it gets to a point where there are instabilities. So there is a temperature on one side, which is different, 2 degrees maybe, than the temperature on the other side. So the energy flows from the higher temperature to the lower temperature, and the wake starts oscillating. You can do it, you can repeat the experiment with whatever you want. And so the flow becomes turbulent. Okay? And actually, that's a nice excuse if you are caught smoking whatever you don't smoke. I was doing an experiment in fluid dynamics, you know. So this is another wake, and this is the wake of windmills in the fog. I don't know where this picture was taken, but obviously the designer of this plant was not a great guy, because you see, this is another, you see, these are all in a row, And if the wind is blowing this direction, the second wheel has a much lower efficiency than the first one. So I don't know, must have been I don't know. He must have been smoking before designing this thing. So what you see here is the wake. What is of interest is the wake. This is the turbulent wake. And you see the same characteristics, almost the same characteristics as you saw in the ocean wake. And the reason is clear. The Reynolds number is almost the same. 50 billions for the ocean wake, 1 billion for the wind. So we are in the same range. And this is the atmospheric turbulence. This is the tropic, of course. If you see, this is Spain, Mexico here. And these are the large turbulent spots which originate the weather changes in the subtropical region. Okay? And that is also regulated by turbulence. This is a hurricane seen from above. And you see that except for the large scale, which is obviously a vortex, there are some small scales here everywhere which don't look like vortices, but are turbulent structures. So, and the turbulence is obviously three-dimensional because you see that here is something coming up. And this is one of the ways that turbulence can be formed. If flow is coming from in this direction, and there is a depression here in the bed of a river, for instance, then the water gets trapped here, but the mean flow pushes in this direction, and there is a pool of water here which keeps recirculating. But why is this water recirculating? Where does it get its energy from? From the main flow. So the turbulence here is extracting energy from the laminar flow to create turbulence. And this is always the case. Turbulence, to be maintained, needs energy. To maintain these motions, needs energy. So if you take away the source of energy that maintains the turbulence, turbulence decays into laminar flow again. Okay. And this is what I was talking about before. This is the laminar flow, this is time, and this is the velocity magnitude. Laminar flow, this is transition where you get these little fluctuations starting, and then you have fully developed turbulent flow, which means that you have an average velocity and fluctuations on top of it. And when you talk about the velocity profile, instead of having the nice Poisson profile, which is a parabola, you have another shape which can also be described by a formula r to the 1/8, but that doesn't mean anything because that's the average velocity shape. But the average velocity doesn't exist in reality in a turbulent flow, because what you see is this. The average plus or minus the fluctuation. And what you see here is something like this. Okay? So this is what makes, for instance, measurements in turbulent flow more difficult. And this is the moment in which turbulence is created. Suppose that you have a laminar flow in flat water, okay? A small river. And there is some gravel on the bottom of the bed of the river. So this creates some instabilities in the flow. But if the bed becomes flat again here, these instabilities, which are called Tolmin-Schlichting waves, they die out because viscosity kills them, makes dissipate their energy. And the flow becomes laminar again. This is air, same phenomenon. There is a hot spot here. Air is flowing laminarly here. The hot spot gives some energy to the fluid and creates these waves. But if the bed here is again at a uniform temperature, this turbulent spot dies out. If there was some more gravel here or some more heat input here, hot spots here, then the turbulent spots will multiply and they would draw so much energy from the laminar flow that the flow would become turbulent. Okay? And will stay turbulent as long as it has some source of energy input. Okay? Is this clear? This is lava flow, obviously laminar. Actually, you can see the quasi profile. See? And this is a volcano ash eruption, obviously turbulent, because the ash is ejected from the volcano at a very high speed. And this is a computer simulation of a laminar to transitional to turbulent jet in a chamber. The boundary conditions are that the jet of methane and air is injected here, and then the jet becomes turbulent, and then there is combustion. Okay? But the idea is to see that the laminar jet, first see these waves here, they exactly resemble the Tolmien-Schlichting unstable waves. But here, there is no damping of this phenomenon, so the fluid becomes turbulent. Okay? Remember, you want, for instance, turbulent combustion because turbulent enhances mixing. So you don't like laminar flames. You like turbulent flames because you want the mixing of the fuel with the air. And when you have a chemical reaction, you want turbulence because it enhances the mixing. Okay? Questions? Okay. So we are finished with turbulence, laminar turbulence, the difference. Since tomorrow, I'm going to talk about flow in blood, capillaries, and in plants. And this flow is always laminar. And we also can assume that the capillaries are tubes, circular tubes. We are interested in studying the relationship between the pressure drop in a tube and the flow rate. And to study this, we resort to the Poiseuille law. Poiseuille law, remember, it's a parabola. And the shape of the velocity is given by, the velocity is only a function of r, and it's given by the delta p divided by the dynamic viscosity, mu, times this, which is r is the outer radius, and small r is the variable here. So it's a parabolic law. To derive the pressure drop, you have to run an energy balance of this chunk. You have a certain pressure here, a certain pressure here, and a volume flow rate Q that flows through. So the pressure difference is given by a force in this direction minus a force in this direction. Okay? And what this is, it is due to some resistance which acts on the flow. We call W this resistance, and this resistance comes out to be with this formula. 8 mu L divided by pi r to the fourth. This should be W. If you multiply this W, resistance, times Q, you obtain the delta P. And this is the famous was a formula for the viscous pressure drop in a pipe. Now, is the pressure drop all we are interested in blood circulation? I maintain no, not in blood circulation, not in heat exchangers, not in sap circulation, not in anything. We are interested in entropy generation, because whenever there is a pressure drop, due to viscous forces, there is entropy generation. See, this morning in the talk, we heard expressions like energy production, energy consumption. I don't like these expressions because energy is conserved. So you don't produce and you don't destroy energy. What you do, you convert energy into a lower or a less useful form, which we call waste heat. That's the problem. When we have the flow of a fluid in a pipe, you have a certain enthalpy here, velocity, suppose, okay? Forget the temperature, velocity. And you have a lower velocity here, or you have a certain pressure here and a lower pressure here for the same flow rate. So where did the delta P times Q work go? Did it disappear? No, because energy is conserved. It went into T0, reference temperature, delta S. So the friction generated entropy, which multiplied by entropy dissipation rate, which multiplied by T gives me a work. G Stodola lost work. I think in thermodynamics you have seen this T0 delta S. It's called the GUI Stodola lost work. If you haven't, look at Moran Shapiro's book and you will see it. Now, so why is this interesting for me? Because I don't care about the pressure drop or the temperature difference. There was another thing this morning, Professor Leonard de Jong, he talked about a heat exchanger where you had a temperature difference on one side which was much higher than on the other side. And he said here you have a high entropy generation. And that is clear because you have a lot of heat flowing through a very large temperature differential, but the heat at 400 degrees is transferred to 30 degrees Celsius. And the quality of this heat is much decreased. You can't do any work. You can produce any work with a 30 centigrade, 300 Kelvin heat. But we can generate a lot of work with a Carnot engine and a 670 Kelvin heat. Okay? So there is entropy generation also in heat flow. And the guy who first gave us rational formulas for calculating the entropy generation rate and the in viscous and thermal flows was Adrien Bejan. And he gave us this formula, I think in 82 or something like that, 82, I'm sure. He said the entropy generation rate in watts per, this is in watts per cubic meter, I think, is given by, or per kilogram, is given by mu, the viscosity, which is the dynamic viscosity, in kilograms per meter per second, times the dissipation function of the Navier-Stokes equations divided by T, and this is the viscous entropy generation. The dissipation function is that function that you never looked at, which is written in the bottom of the page of the Navier-Stokes equations, and which looks like du squared over dy, du over dy squared, plus dd over dx squared, plus du over dx plus dv over dy squared. Okay? This is, and then there is w as well. So this is a dissipation function which is always positive because it's a sum of square terms. And multiplied by the viscosity, divided by temperature, you have the entropy generation due to viscous actions. This can be translated into pressure times flow rate, and you get a formula like this. Okay? There is a mistake here. This should be capital R, which is the radius of this thing. Now, there is an additional form which we are not discussing here, and because we are discussing tomorrow, I'll be discussing only isothermal flows, and which is due to difference in temperature. And also, lambda is the conductivity of the fluid, and this formula is the gradient of the temperature. Also, you have a formula like that in fluid dynamics books. Now, I'm interested in this because the flow of blood, if it creates through my body, if there is any irreversibility in this flow, then my heart has to make up for it. Okay? So I have to use metabolic energy to feed my tissues with blood. So the lower the entropy generation rate in the blood system, the better it is. And I'm going to study this, I'm going to discuss this item tomorrow. So, and I need this thing tomorrow. There is one thing which I'm not considering here. Permeable walls. Why? Because it's too difficult. Now, Professor Leonard, again, talked about membranes which are permeable to some molecules and not permeable to other molecules. We are trying to repeat, to build these membranes artificially, but nature is based on these membranes. Plants, organisms of any kind, our bodies are filled with these membranes. And one of these membranes is in the wall of the capillaries. This is a red cell. The red cell flows through the capillary, but the wall of the capillary is permeable to certain items, not to the red cells, but to certain items that have to get into the tissues. Oxygen, for instance, and nutrients, and vitamins, and hormones, or amino acid, or sugar. And also to CO2, because CO2 is gotten into the capillaries, which take the, let's say, the dirty blood back to the heart. Okay? So the capillaries have to be permeable in two directions to different stuff. And they are. So what happens when I include, suppose that I want to include permeability in this picture. Then I have a concentration here and a different concentration here. Different Gibbs enthalpy value. Which means if I have a flow in this direction, I have an entropy associated with this flow as well. So I should go back to the previous slide and say there is another term here, the entropy of permeable walls. But it's a very difficult term to compute, so I skipped it. Okay, I'm not considering it. Now, this is actually what I'm going to talk about tomorrow. So we have to understand how plants and animals circulate their substances. This is a schematic representation of a tree. The roots suck some water. Actually, they don't suck some water. They are permeable membranes. And they absorb water and nutrients from the ground due to the different concentrations in the ground and in the root. So it's a permeable membrane again. And then this water, mostly water with nutrients, is supplied to a system which is called the xylem or xylems, a lot of small pipes, a myriad of small pipes that bring the water up to the tree, to the leaves. You know how this water is transported? Capillarity. Capillarity, though, would bring the water up to 9 meters, 10 meters only. Okay? How do plants which are like 30 meters high, they combine another capillarity with another action, which is called the ionic movement. These are items which are being studied right now. Suppose that this is the wall of the xylem. There are points in which the molecules of the cells of the xylem get hooked to the polarities of the water, and then they release the polarity. So the water is actually walking up this ladder, so to say. And these cells are obviously using their biological energy to do this. Okay? So it's a very complicated issue. However, we will neglect it. The water flows up somehow. Okay? Flows up and gets to the leaves. When it gets to the leaves, the water and the nutrients are subject to the photosynthesis. So by using the ultraviolet spectrum, they are processed and become glucose, mostly glucose, and some other vitamins. And then two things happen. First, the remaining water with the glucose and the nutrients is sent to the other parts of the plant, which have to be fed. Okay? The plant has to grow. So they grow by this mechanism. And the water is released because the leaves have some valves that suddenly open and blow off the water, evaporate the water. It is said that plants sweat. Okay? They evaporate. And they do. And this evaporation produces an osmotic pressure which helps carrying the water through the pipe. So there are three combined actions there: evaporation, capillarity, and this polar motion of the molecules. So this sap that flows down through a system which is called the phloems. And of course, in a plant, there are millions of these pipes. And the best thing, I think, is representation of a leaf. And you see this network. This is a main xylem coming here, and then it splits into 2, 4, 8, 11 bifurcations here, and then it gets into other bifurcations. That is a network of xylems that bring water and nutrients to the rest of the plant. And then there is a hidden, we don't see it here, a network of phloems that takes the products of the photosynthesis back to the plant. And here, the type of connection is very clear. It's a network of channels. And actually, you can see it when you cut the wood. The xylems are in the center and the phloems are on the external side. And in dead wood, this is the xylem side, see this cells, and the phloem is underneath of the bark, because the phloems take the nutrients to the wood that grows. And inside, the wood is dead. Okay? The new wood is outside of the trunk. So this is the circulatory system of a plant. And in the body, it's very similar, except that we have a pump. But the pump, the heart, pumps the water through the aorta, the blood through the aorta, and then it goes through smaller arterioles and through the whole body, bring the nutrients, extract the detritus from the cells, and take it back through the veins to the heart to be put in circle again. Okay. And the system works like this. The blood, which has oxygen and comes from the heart, flows through the main arteries and then through the smaller arteries until it gets to arterioles. The flow in the main arteries is tubular. The flow in the arterioles is laminar already. Then from the arterioles, the blood gets into capillaries. The capillaries have two functions. Let's follow one of the capillaries, this one. In this portion, the blood provides the tissue around it with oxygen, nutrients, and whatever it needs. Okay? In this portion, the capillary extracts from the tissue the organic detritus. All of you, those of you who have practiced some sport, know that if you run the 400, 800 meters, 800 is worse, you get this lactic acid in your, you can't actually move, you can't walk, okay? Why? Because this lactic acid, which is a byproduct of muscle action, has accumulated, and your blood flow is not enough to remove it. So why do you practice? Why do you train? You train to increase the blood circulation specifically for that action. Okay? So the blood, this here, removes all the detritus from the cells. Notice that mass flow rate remains the same. So here I have a certain mass flow rate, I lose some up to here, but then I gain some again up to here. So the mass of the fluid which circulates remains roughly the same. Of course, we have literally millions of these capillaries in our bodies. And the reason for which I'm interested in, well, the talk tomorrow is about what it is that these capillaries, which are laminar, they have a function like this. These red cells flow in a laminar flow through the capillary. This is another capillary junction. And then there is a bifurcation. And if you look at plants or capillary bifurcations. People have been looking to those bifurcations for centuries. And from the beginning of 19th century, 20th century, 19-something, people were interested in this issue. If you look at trees, for instance, the branchings of the trees, they're all the same. They look the same. Okay? Even leaves, they look the same. And if you look at tissues and look at the capillaries, the branchings look very similar to each other. So there is an interest in understanding why they are similar to each other. Is there any physical reason? Is it by chance? Or are they not similar to each other? It's only, it looks to us that they are similar, but if we investigate better, they are not similar to each other. This is an important issue, I think. So what I want to do tomorrow is to examine this. Suppose I have a bifurcation. If I have two pieces of capillary in series, then the pressure drop is given by this formula. The resistance of the complete branch is equal to the sum of the resistances. If, however, the branches are in parallel, like in bifurcation, then you know from fluid dynamics that 1 over the resistance is equal to the sum of 1 over the resistances of the individual branches, and you get a different formula. So if you have a complete bifurcation, you have this in series with this, but this is given by this formula. And so you obtain this formula here. But look at this formula. L0 is this length. R0 is this radius. R1 and R2, suppose they are the same, okay? They must be smaller than R0 because they are carrying the half of the blood, okay? But if they are smaller, their resistance is much higher. If they are the half, the resistance is 16 times higher, 2 to the 4, okay? So there must be, because bodies and plants are not made, nature doesn't work by chance. Well, nature works by chance, but evolution is a very selective tool. So it's unlikely that if two plants evolved in a way that one had a very high entropy generation here and another had a very low entropy generation, the one with the high entropy generation survived evolutionary-wise. Why? Because the other one, with the same amount of solar energy, would waste much less energy to grow. Is this clear? No. Yes or no? Repeat. So it was not clear. Suppose I have two plants. Let's say two bifurcations. Okay? They carry the same amount of blood or sap in a plant. One has a shape, radius, length, you know, such that it produces twice the entropy generation rate as this one. But they both get the same solar radiation. So this one gets 1 joule, has 2% of waste energy, uses 98% for the growth. This one gets 1 joule, has 5% destruction, gets only 95% for the growth. Over a million of years, evolution will lead this to extinction, and only this will prosper. So we may think, that the plants that we are seeing today have developed the best possible evolutionary shape. And of course, also our body. Okay? So this is an interesting topic. This is what I'm going to talk about tomorrow. And the problem is this. People have been studying these branchings and these things. And there are two types of laws that came out. One is isometric law. Isometric law is geometric similarity. Okay? A sphere is a sphere, whatever the radius is. And the volume of the sphere is always equal to 4/3 of the square, the cube of the radius. The sphere is this, or like this, or the sun, it's the same thing. This is an isometric law. Examples of isometric law, they are also in nature. There is a snail. I was told you call it carapajo? No. What do you call a snail? Caracol. Caracol. I'm sorry, caracol. Carapajo is another thing. Is the thing of the crab. Okay, a caracol. There is a species of caracol which keeps a certain shape when they grow. They keep the same shape. They grow isometrically. In that case, it is correct to say that the volume is equal to the height to the third, which doesn't mean that it's equal to, but it's isometrically equal to. So there is a constant that multiplies the height to the third, okay, to the cube. The constant may depend on location, okay? So the volume of the snail is 1.5 h to the cube in one location and 0.3 h to the cube, but still it is an isometric law. The shapes are the same. Another example, this is in gas turbines. You can look at this. I leave this here on the computer so you may use it. The shape of all blades looks similar in a certain gas turbine, and particularly they depend on H over L. So you can say that H is isometrically proportional to L. H being the height of the blade and L the chord of the blade. Okay? You can formulate thousands of these laws, but how do you check them? Well, they only check that there is a theory, of course, behind any law. Okay? Somebody got up one day and looked at many snails and said, look, this snail has the same shape as this snail, so, and this too, so there must be a general law. There is always a theory, a model behind the law. So the only way to test it is experimentally. And if you do this, you see that in the first example, the snails, the slope of the log volume over the log of height is 3, because the experiments fit the law. So the law is confirmed. But in the second example, if you plot the L, the chord, over the H, the height of the blade, then you see that for different turbines, there are different aspect ratios. So that law is obviously wrong. There is some parameter that we didn't consider. So the only way to check whether a law is isometric, an isometric law applies, is to run some experiments. But even if natural structures do not evolve like with isometric laws, according to isometric laws, they may still evolve according to allometric laws. Allometric comes from Greek, allos, different, metric, measure. Allometric scaling is actually quite common in natural artifacts. This is an example with crabs. Okay, there is a certain type of crab that has a fixed ratio. This is our assumption between the length of its pinch and the body size. So what you say, if this ratio is supposed to be 0.5 or whatever it is, this is the theoretical line. This is the measured, the result of the experiment. So the law is allometric for sure, but not with the shape that we thought. Not with the one-to-one ratio, but roughly, as you see, when this is the body size. So when the pinch is like 2, the body size is more than 2. So the law is, the coefficient of proportionality is lower than 1. And this is another example. The body size versus the brain or heart size. Let's look at the heart. The assumption is, according to a theory, that the heart size is proportional to the body size. Why? Because the amount of blood that you need to circulate through the body grows with the volume of the body. So let's test it. It's an allometric law. You test it. You test it, and you see that almost fits the line. Another theory says that the size of the brain is also proportional to the body size. And why? Because the brain grows with the age. There is a theory behind it. You test it, and you see that that's not true. after a certain body size, which corresponds to a very early development in the child, the brain size is almost constant with the body size. Okay? Not more intelligent, but there is an incongruency here, because they show that the brains of women and men have the same size, and I don't believe that. So, I'm sorry. Joke. This is a broma, okay? So, this law is rejected. The theory might have been convincing, but the experiments don't convince, okay? So, this is the way you test the allometric law. And I think this is all. What I'm talking tomorrow, those of you who are coming to my lecture, well, you have to, so all of you, sorry for you. There is a law which has been developed starting from the beginning of the 19th century, which says that there are certain ratios between the radii of different branchings in capillary flow. This law has been exploited it's called the Hess-Murray law. This law has been exploited in the design of technical structures and interpretation of natural structures, and the main proponent of this theory is a friend of ours, as a matter of fact, Adrian Bejan, who is a very famous thermofluid dynamicist. Convection, heat convection. Yeah? Yeah. Very difficult book, by the way. Very difficult book. Difficult, yeah, to teach from. So, however, I will try to convince you tomorrow that Adrian's theory is based on a law which is not correct. It's an allometric law which is not correct, and I'll show a different energy balance which leads to a different law. Okay? So this is why all of these topics were important. These were like introductory topics to the talk tomorrow. Okay? Thank you very much. If you have questions. There is a question. Yeah. This is a really good question. All these laws do not consider the unsteadiness of the flow, including my treatment tomorrow. But of course, the fact that the Poiseuille flow is unsteady introduces another entropy generation term, which you have to consider if you want to build a more complex model. So there are two issues which have to be considered. First, actually three. First, the permeable wall. Second, the transient, the periodic flow. Third, the fact that the wall of the capillaries is not a solid wall, but it goes like this when the blood is pumping. So this is a much more complicated treatment than we can do here. And what I will show you tomorrow is just the first approximation. Okay?
Ahorita en español para los chavos que están en Irapuato, porque para que entiendan el concepto, en los últimos 15 a 20 años, en la comunidad científica, la de avanzada, la que va en la punta del conocimiento, ha habido mucha discusión acerca de si la teoría de Adrián Villán, que no está en los libros, no está en el libro de convección, eso está ya más avanzada, que si es correcta, él está empujando fuertemente. Tú lo saludas y lo primero que te pregunta es, ¿no has hecho nada en teoría conceptual? O sea, su teoría conceptual lo que anda empujando fuertemente. Entonces, aquí hace años, incluso en nuestro grupo de investigación, hicimos un ejercicio por mucho tiempo, unos 4 o 5 meses, de discutir si la teoría de Adrián Villán era realmente la ley, porque él le dice ley conceptual. Y entonces, pues Enrico también, con algunos estudiantes de posgrado que tuvo, también se dedicaron a, no con palabras, sino con cálculo, a ver si realmente la teoría conceptual era ley conceptual. Y entonces hay gente que está muy pro o gente que está en contra. Yo le decía a Enrico que yo siempre consideré que era un corolario, y hace rato más o menos quedamos de acuerdo que él también considera que es un corolario. Entonces lo que está presentando aquí, yo los invitaría a que le tomara mucho, no sé, sabor de discusión. Va a continuar Enrico, de acuerdo a lo que estamos platicando, va a continuar esto porque les va a dejar un proyecto. De ese proyecto, así como el doctor Kowalski les va a dejar, va a depender que vayan ustedes a tener un diploma que llevaron un taller con él. Entonces él va a dejar una tarea. Por eso es la invitación y por lo cual quise intervenir en español, para que todo el mundo quede informado. Digo, un estudiante de posgrado, eso en su currículum, decir que llevó esto, pues luce bien. Entonces, para que le ponga mucho interés, ¿no? Esa discusión que hay entre ley alométrica, ley biomimética, ley de la regla dorada y la teoría de Adrián Villán. Entonces, para que ahorita, si quiere incluso dedicar a otras preguntas más a fondo, aprovechen ahorita. Enrico, por mucho tiempo, en los últimos 20 años también, se ha dedicado a debatir esto. Entonces, y a debatir con cosas concretas, un intercambio de calor con este tipo de arreglo, el cuerpo humano, siguiendo las cosas del cuerpo humano, aplicado a cosas prácticas. Entonces, aprovechen ahorita, y porque se va a venir un proyecto, entonces, para que mañana estaría, tomorrow you will be finishing up giving the project, right? So, entonces pónganle ganas ahorita, traten de ver qué más información. Si no habían oído hablar de leyes alométricas, pues ya lo está introduciendo. Si no habían oído hablar de leyes biométricas, también de eso está hablando, entonces, para que entren con muchas ganas, ¿no? Go ahead. That was just to ask them to have questions. I mean, to take everything that they can take, you know.
No, actually, I showed you that there is this term because that's a very important term. So in a theory, you have to include it, okay? Because let's say from a principle point of view, it's a very important term because the flow goes through and then comes back on the other portion of the capillary. The problem is that A, it's very difficult to compute. B, the effect, the numerical effect is very small. With respect to the pressure drop, it's a very small effect. So you can neglect it. But first, before neglecting it, you have to make an assessment of how important it is. And I've done that in other papers before this presentation. So I know that the effect can be neglected at this level. Mm-hmm. It's if you think of the term in the entropy production, it's always a viscosity times a dissipation function divided by a temperature. Okay, for the thermal effects, conductivity times a square of the gradient of temperature divided by the square of temperature. For the mass permeability, it's a diffusion coefficient or permeability coefficient multiplied by a difference of concentration squared divided by a temperature. Now, the difference of concentration in the capillaries is small, because obviously it has to be small. We cannot have a part of our body with sugar and a part without sugar at all. And second, the diffusivity coefficient is very low. So the product of these two is low. So we know that it is low. Okay? Does it answer your question? Other questions? Even in Spanish. Come on. Yeah. It's a good question. Well, first of all, in the panel, I was meaning something else, and I can explain it now. But the immediate applicability of this thing is in the design of small heat exchangers. We are now approaching a limit in the design of computers. The chips are becoming too powerful, and they dissipate too much heat per centimeter square. So we need more and more efficient systems, cooling systems. And if we can develop small heat exchangers of the size of a chip, which can extract the heat from the chip, it would be like you have the chip and then the heat exchanger on the bottom of the chip. So the heat exchanger has microchannels. These microchannels are laminar. So if you reduce the entry production in these laminar microchannels, you get a lower pumping power, but a higher heat subtraction. So that's an immediate application. Okay? Is this clear? What I was, in the panel, I was referring to something different. Like, for instance, these are very far-fetched. Like, think of a forest, okay? Natural forest. You have apple trees, cinnamon trees, whatever, palm trees, whatever, okay? A mixture of trees, they all grow together, okay? And no species kills all of the other species. They grow together because they have a sort of cooperation on a natural scale, okay? Even when they die, their detritus is food for other plants and for other animals. So this is what is missing in our organization, I think. Not the dead, but the fact that we want to have one field which delivers only corn, one field only strawberries, one field only palm, and so on and so on. But this is against the natural development things. Of course, we are forced to do that because we need a lot of corn, a lot of strawberries, and so on and so on. But there should be other means to get the production, even in agriculture. Yeah, yeah. A more rational production. And I think the most natural way, the rational way, is to look at nature. Because nature has been selected through evolutionary pressures in a way that was very, very strict. Dinosaurs died, you know. Many species died because they were not up. Still today, you say that there are some species which are dying. Of course they are dying because they are not capable of adapting to the new structure of the changing structure of the microclimate. So we should take example from that. That's what I meant in the panel.